Okay, hello everybody. Today I will present MANUS. This is Markerless grasp capture using articulated 3D Gaussians. Yeah. So as we can see here, we'll have as a result accumulated context between hand and the objects. Okay. So MANUS paper includes MANUS hand, efficient representation for articulated hands using 3D Gaussians, a method that uses MANUS hand and 3D Gaussians to represent the object, and MANUS grasps. This is a large data set that contains 50 plus cameras, 360-degree coverage of grasps, and 30 everyday life scenarios. Yes. So dataset includes 360-degree coverage, 7 million frames, 50 plus cameras, RGB color, also ground truth contact using wet paint, and 2D/3D hand joint locations and segmentation masks for object and hand. Yes, here's the pipeline of MANUS. So at first we will initialize our Gaussians. Then to get the post Gaussians, we will use forward kinematics and linear blend skinning. After this, we will render the image, calculate the loss, and optimize Gaussian field. Yes, so MANUS hand consists of 21 bones and has 26 degrees of freedom. Yes, so we can see the picture here that show us the degrees of freedom and all the joints. For getting the joint positions and the skeleton of the hand, we will use existing methods like alpha pose and inverse kinematic fit. So alpha pose gives us the joint positions, and inverse kinematic fit will give us the skeleton of the hand, as we can see on the picture here. So all the joint positions and skeletons already included in the dataset. So how can we calculate the Gaussian positions in post space? So for this, we will use forward kinematics and linear blend skinning. So forward kinematics will just give us the position of the Gaussians using the positions and angles of the joints, and linear blend skinning also will output the position of the Gaussians. So because Gaussians are unstructured, we cannot assign weights like usual. So we will assign skinning weights to the 3D grid first, and then we will assign skinning weights to Gaussians by using trilinear interpolation. So we will just see the position of the Gaussian. We will see the the nearest grid cells that are near this Gaussian, and just have the mean of those grid skinning weights assigned to this Gaussian. Yes. So by using linear blend skinning, we can get the Gaussian cover, position, and covariance. After this, we will render the picture and calculate the loss. So in calculating the loss, we will use this type of loss functions, like the structure similarity loss, perceptual loss, and isotropic regularizer, which kind of regularizes how big and how small the Gaussians can be. So min S and max S here is the minimum and maximum scale of the Gaussians, and S is equal to 0.4. So this will make all the Gaussians appropriate size. So now we can optimize the Gaussians and we can get the positions and the colors of the Gaussians in pulsed space. So we can use the grasp capture now. We will calculate the Gaussians of the object and Gaussians of the hand. After this, we will just see the difference, the distance between Gaussians of the hand and Gaussians of the object. And if the distance is small enough, it is considered as a contact. So here we have 3D contact map, which is equal to the distance, if distance is smaller than some threshold, and 0 otherwise. Yeah. So here's some results. As we can see here, we have static objects and the context here. So this is the context that MANO has, and this is the context that MANUS hand calculated. And we also have ground truth context. We obtain ground truth context by wet paint on the objects so that the paint sticks to the hand, and also after this we can kind of visualize the context, accumulated context. Yeah, as we can see here, the MANUS hand is a little bit more accurate than other methods. There's another representation of the method. Also, here we can see the misalignment of the Gaussians, and we compare it with MANO. It's actually quite decent and accurate. Here again, the comparison with MANO. So green, I believe, is MANO, and yellow is MANUS hand, although it's almost the same. So this method has some limitations. For example, we can do this only with static objects, because we can't move the object in the space. Also, manipulations are only for short time frames. And the method does not consider the skin stretching. Here we can see the visual representation of the 3D Gaussians. So this is all. Do you have any questions?